PhD student with Monash University. Before joining Monash, Mitra completed her master degree in food chemistry, where she worked on the oxidative stability of edible oil and suitable for daily consumption. Here at Monash, Mitra worked on the encapsulation strategy for food application, especially using the oil and fat as a carrier. Mitra, please.
Hello, everyone. Thank you, Yang, for the introduction. Today, I want to give you a brief snapshot about one part of my PhD project, which is about physicochemical characterization of solid lipid particles composed of fish oil and milk fat. First of all, I want to explain a bit what is omega-3 fatty acids. Long-chain omega-3 polyunsaturated fatty acids, especially EPA and DHA, which exist in fish oil, are among the most important nutrients having a lot of health benefits to humans. They play an important role in reducing the risk of cardiovascular diseases and promoting visual developments in infants. Therefore, foods enriched with these fatty acids are gaining importance in food markets. However, there is always a challenge for food industry to incorporate these fatty acids into food products. Why? Because these fatty acids are extremely unstable toward oxidation. This vulnerability comes from the high number of double bonds in their structure. So these number of double bonds lead to oxidation process, and when the oxidation happens, we will have a number of different chemical compounds. They can be toxic, and at the end, they can lead to the development of some undesirable flavor, and potentially at the end can lead rejection for the consumers. So a number of strategies have been applied till now in order to improve the oxidative stability of fish oil and at the same time mask the fishy odor. For example, from oil modification category, we have adding antioxidant, hydrogenation, interesterification, fractionation, and also blending. All of these processes has their own pros and cons, but for blending, we can say that blending of fats and oils is the simplest method which can be done in order to attain particular stability, sensory, and quality properties. Moreover, this process can be applied as a pre-treatment to optimize oil and fat mixtures to provide specific properties for encapsulation technology. Among all the encapsulation technology, as all of us would know, spray drying and freeze drying are so common, and they have their own disadvantages. For example, we use high temperature in spray drying, and freeze drying would be so costly for food industry. Among all of them, spray chilling is considered as the least expensive one in food industry. It is a free physical process used to produce solid lipid microparticles. Also, the most suitable carrier for a spray chilling would be a tag composition, also fatty acids, alcohols, and waxes. And now I want to give you a brief introduction about how this spray chilling works. As I mentioned, we use carriers which are mainly lipid. We can use milk fat as a carrier for this process. The carriers that we use need to have the melting point above 34 centigrade. The whole process is somehow similar to spray drying. The difference is we use cold chamber instead of hot chamber. Also, the active agent that we need to encapsulate should be dissolved in lipid. For example, it can be fish oil, it can be fat-soluble vitamins, it can be some probiotics. And how this system works? We mix the carrier and active agent at the temperature above the melting point of the carrier. After they mix completely, we inject them inject the molten mixture into a cold chamber. As you can see here, we inject it into a cold chamber, and then the active agent and carrier solidified so quickly. And then we have the microparticles at the end. So one of the main characteristics of the microparticles produced by a spray chilling is they have microsphere type. As you can see here, the white spots are active agent and the dark part is carrier. As you can see, the active agent dispersed all over the particle. It can be on the surface, it can be in the core, so we can say that it's completely concentrated in the core. And this is the reason that one of the main drawbacks of this process comes. When the fats and oils, the molten mixtures congeal too fast at the chamber, the lipid matrix sometimes crystallize into an unstable arrangement. So this phenomenon can change the particle structure during the storage. So when the particle produced at the end of the spray chilling, during the storage, this unstable crystalline structure has this tendency to transform into more stable crystalline structure. And then the active agent can come out of the particle, which core expulsion happen. A brief introduction about milk fat. Milk fat has 60% saturated fatty acid. It has a melting point above 37 centigrade. Also, it has a complexities in crystalline structure. Based on the condition, milk fat can have a variety of crystalline structure. Also, the capacity to entrap low melting point oil, such as canola oil and fish oil, was reported in the literature as well. And another main important characteristic of the milk fat is it has unique and pleasant taste. Also, based on our previous research, we noticed that adding 30% or more milk fat to the blends demonstrated relatively a stable characteristic resembling milk fat. So till now, based on the literature, there is still lack of knowledge about the possibility of having milk fat to entrap the fish oil, to change its characteristic, and to mask the fishy flavor by a spray chilling process. And the final solid lipid particle with the mixture of milk fat and fish oil can be used in dairy industry and can be used in lots of products that we usually store them in low temperature, such as ice cream, such as chocolate. So in order to fill this gap, what we did, first we prepared the molten mixture. We blend fish oil and milk fat at various concentration, and then we analyze the oxidation for the overall blend to see whether the overall oxidative stability will improve or not. We measure peroxide value as primary oxidation products and TBA value as secondary oxidation products. And at this stage, we produce solid lipid particle by single droplet method. We produced a blend and we immersed it in liquid nitrogen to have the particle. And then we analyzed the thermal and structural behavior. So here you can see the milk fat and fish oil characteristic. So what is important for us is the tag composition and fatty acid percentage. For the fish oil that we used in our study, you can see the fish oil we used had around 30% long chain omega-3 fatty acids, around 27% DHA. Also, the fish oil we used had around 64% unsaturated fatty acids. How about the milk fat? The milk fat that we used for our study had around 70% saturated fatty acid and just 2% polyunsaturated fatty acid, which give us the information that the milk fat that we used in our study was completely stable. After that, we analyzed the oxidative stability for the liquid. at 80 centigrade. As you can see here, the peroxide value after 300 minutes and also the TBA after 300 minutes for the pure milk fat and pure fish oil. And when we mix them with the percentage of 50-50, I just showed you this data here, you can see that yes, the peroxide value decrease, the TBA value decrease. So the overall stability, we can say that it can be increased by adding milk fat. After that, we produce the particle. As you can see the shape of the particle here, and again, because we produced it by single droplet method, we wanted to be sure that during the process, whether we have any loss in fatty acid percentage or not. So we analyzed the fatty acid composition by GC, and as you can see here, the red columns are for the chilled particle and the black column was for the liquid. You cannot see any significant difference in fatty acid composition. So during the process, nothing happened to our EPA, DHA, and also the saturated fatty acid. So the whole fatty acid composition would be the same. After that, we analyzed the melting behavior. DSC analysis has been conducted for the blend of 50-50. As you can see, the melting point were different for two states. The black line is for the particle state that we start heating the particle from the temperature of -20, and the red line is for the particle after deleting the thermal history. So it didn't have the shape of the particle. As you can see here, the first melting point appeared at -4.55, which was absent in the particle state. Also, another melting point at around 7.84 centigrade, which was again absent in the particle state as well. In the particle state, it seems that phase transition didn't occur for low melting point tag molecules until a high temperature was reached, as somehow low melting point tags of fish oil may bond with other higher melting point tags of milk fat. Therefore, the different melting point of liquid state would have been due to the alternative arrangement of these tag molecules. Also, you can see that all the melting points in the particle state shifted to higher temperature when comparing with the liquid state. So this is another, it can be another reason that it seems that there is a change in tag composition during the melting. Also, the melting behavior of the spray chill particle was examined in hot stage microscopy. The sample was heated from -5 to 60 centigrade with the heating rate of 10 centigrade per minute. You can see the shape of the particle. These particles are the blend of fish oil and milk fat, the 50-50 blend. So, and the changes in the particle structure recorded by the camera. As you can see here, hot stage microscopy often combined with DSC to characterize the thermal behavior in solid state. As you can see in the figure, the particle retained its shape until 27 centigrade, which is really interesting for us. And it began to melt at 31 centigrade. It seems that in particle form, most of the high melting fatty acids, high melting tag composition distributed on the surface, allowing the retention of the shape and preventing the melting. So, in conclusion, till now, I can say that the blending strategy with milk fat as a stable fat can be used as a pre-treatment to improve the overall oxidative stability. Also, during the formation of particle, tag molecules of milk fat and fish oil may rearrange into different structure, which help them to be more stable in terms of melting points. Also, based on the actual melting point of the particle at around 31 centigrade, there could be a possibility of having high melting point tag molecules on the surface and the low melting point ones in the core, which still needs further investigation. And at the end, I want to say thanks to all my supervisors, especially Professor Cordelia, Professor Victoria, Professor Mengwei, and Dr. Young for their support, all my group mates and friends, also Monash University for funding my research, and thanks to all of you for your attention.
Okay, thank you, Mitra. And does anybody have any question? Well, waiting for someone to type or unmute their questions. I have a question for you, Mitra.
Yes.
I know you are using milk fat as a carrier. That's a connection with dairy industry. But do you think it's possible that you can use this microcapsule in any types of dairy product in the future that's produced from milk fat and add to like yogurt? Do you think it's possible or any other type?
Actually, I think it is possible to use it in dairy products as, for example, such as ice cream, or such as yogurt. Yes, it is possible, but it depends on the temperature that we usually store it. It is really important because we want to prevent the change in crystalline structure. Also, we want to prevent melting. But so I think for dairy products, which are usually stored in temperature below 4 centigrade, these particles are suitable to use, yes.
Great, thank you. I see Matilda has one question. Matilda, can you go ahead and unmute yourself?
Yep. Can you hear me?
Yes.
You mentioned that the surface distribution of fish oil in these matrix type microspheres, right?
Mm-hmm. Yes.
Have you tried any, like change the ratio of the coarse material and the warm material, or change the speed rate of spraying to, reduce the exposure of fish oil?
Yes, true. This is our aim now, because now we use liquid nitrogen in order to solidify the particle. But for sure, because it is crystalline structure on the surface, and generally because it is just a mixture of lipids. So by changing the temperature, by changing the condition, we can change the distribution on the surface. This is something that we aimed. Maybe we need to increase the temperature of the chamber. For example, instead of using liquid nitrogen, using another liquid with higher temperature, to see whether this distribution and whether this melting and thermal behavior will change or not. Yes, this is one of our aim.
Okay.
To do it in the future.
And also, you mentioned that you would like to incorporate your lipids droplets into ice cream. When I listened to this idea, I was so surprised, because I cannot imagine a fish oil flavored ice cream. So have you ever smelled your lipids? Does it smell like ice cream?
Yes, this is one of the benefits, because milk fat, you know, that we can smell the milk fat flavor, the flavor is so strong. And whenever we mix these two together, even when we have high percentage of fish oil, for example, when we have just 30% milk fat, we can notice that somehow the fish oil flavor disappeared. So with
mask off.
Yes, exactly. We can with the help of this spray chilling, especially with milk fat, because of its pleasant flavor, we can mask the fishy odor. So this is the reason that this can be added into some dairy products without any fishy odor.
That makes sense.
Yes.
Impressive. Thank you.
You're welcome. Thank you for the question.
Okay, thank you, Mitra. I didn't see any other question. If anyone have further question, please type in the group chat, and Mitra, you can follow up with that. And we are just on time for our last speaker in this session, Ken Fun from the University of Queensland. Ken, do you want to share your screen while I do the introduction? Ken has been working at Department of Biochemistry at Nông Long University, Vietnam since 2013, focused on novel technology to enhance quality and safety of food. And Ken obtained the Bachelor of Engineering, Chemical Engineering from Nông Long University, Vietnam, and the Master of Science in Food Science and Technology from Chiang Mai University, Thailand. Currently, Ken is a PhD student with University of Queensland under supervision of Professor Bess Bandari, working on the application of nanobubbles in food processing. Please go ahead, Ken.
Sorry, just unmute my voice. So good afternoon, everyone. Can you hear me? And thank you very much for your kind introduction, Young. Actually, my connection is not good, so may you allow me to just turn off the, stop the video, and then I just continue sharing my presentation slide. And then,
yeah, please, that would be better.
Because my connection have some problems. So, is it the slide is on the screen? Yeah. So again, good afternoon, everyone. My name is Khan, and I'm a second year PhD student under the advice of Professor Bess Bandari, Dr. Tuyền Trương, and Dr. Young Wang, the chair of the section today as well. So my presentation today is about the generation of CO2 or carbon dioxide nanobubbles and their application in food viscosity reduction. So how we can apply or using the tiny bubbles by CO2 gas to get the reduction in the viscosity of liquid food. So firstly, what is the nanobubbles and how we can differentiate them from the other like macro or micro ones? So generally the difference is from the size scale. So we totally have the three main type of the bubbles, and nanobubbles is the smallest size range, which range from just about like 10 or 100 nanometer up to about under 1000 nanometer. So it's very small, and the tiny extremely small in diameter offer them some prominent characteristics, such as they can longer stable in aqueous solution, and they can offer very high specific surface per volume ratio, together with some other behavior like colloidal suspension in medium, and also they can scatter the light, which we can use as well to determine the size or measure their existence in the liquid or the aqueous solution. And outside the gas nanobubble, they call the ionic layer, which offer them quite high stability and also the high value, absolute value of the zeta potential. So there are many or massive range of application of nanobubble across the industry, where they are incorporated or possibly be incorporated. For example, in water treatment, many research already apply industry. They use the ozone nanobubbles to treat the water or cleaning the surface without using of other chemical or detergent substance. And also, for example, like after treatment with oxygen nanobubble, the plant grow very well. And one of the interesting I found here is they can put the sea water and the freshwater fish into the same pool, into the small container. and they can live and grow very well together, which is quite impossible in the nature. And for how about the food sector? So actually, the incorporating of gas into food have played a long time have played a vital role in determining the stability, microstructure, and functionality of many different food products like carbonated beverage, bakery, dairy, or confectionery products, and establishing the relationship among the process, product, and functionality. However, most of the application here is just in the micro scale, and there are still minimal studies on the nanobubble usage in food related or food concerning or related application. So our work will focus on the generation of the food grade gas nanobubble in the continuous mode, because we would like to apply them more easily in the large scale situation in food area. So we focus on the continuous working system. And the first one we use it is from industry as well. They call the Stoney series nanobubble injection system. And here the schematic of the generator, the one that can make the nanobubble or the tiny gas bubbles. So how it works for operating the gas, we can see here the gas is firstly introduced or go into the system to reach the setting gas pressure and gas flow rate. Then when the gas is confirmed, the water is pumped throughout they call the injector right throughout the cell. And the obtained good state that we found already is the gas pressure is about 4 bar, with the gas flow about 4 liters per minute, the flow of the CO2 gas, and the liquid to pump the liquid pressure, which is used to pump the liquid throughout the cell after the gas introduction, is about 2 bar. And the outlet is mean the water containing the nanobubbles here, it can have the CO2 concentration up to 2000 ppm. And we just got the outlets very quickly, just a lower or just a 30 seconds or 1 minute, and we get the outlet liquid. And the pH is lower than 4, it's here just a 3.5, it's quite low. Then the generated nanobubble obtained by this commercial system can exist. We test the storage periods, can it exist or not, and then it can exist with the 100 nanometer scale up to 7 days. And because we put the solution or the nanobubble water into the untitled container to see whether they can exist or not, so the concentration of CO2 gradually be reduced, but it can still up to or nearly 1000 ppm after 7 days, and the pH still remain lower than 4 with the higher zeta potential value. And the notice we just back in here, just the quantity of gas should be mixed in water as high level enough to maintain the stability of the gas nanobubbles. In the next step, we check whether when we combine or put the electrolyte and surfactant into the water medium, and how it can affect on the formation or the existence of the nanobubbles. In here, we use different concentration of the test substance, as most of them here is lower than we call the transition concentration coalescent or reticle micellar concentration CMC, because we would like to see the change in the property of liquid medium with and without the existence of nanobubble rather than with the existence of the surfactant or the salt. And we can see here in the graph, the number side distribution of CO2 nanobubble generated in water containing different concentration of electrolytes and surfactant are different. There are some good impact, like we put just a small amount of salt, or we use the ionic because the outer layer of the nanobubble is negative charge. So if we use ionic surfactant or just a small amount of the salt, they can have to get the better signal of the side distribution. While if we use just the other salt with the calcium chloride, because when it dissociates in water, it makes to the 2 positive charge, it dissociates into cation, or we use the twin, they not the observed result is not good because there's a quite more positive charge combined, or just see only the molecule side of the tree, not the signal of the bubbles, because they don't have charge. It's just the non-charge or non-ionic surfactant. This slide shows the surface tension, gas concentration, gas amount of and pH value of nano water generated by different concentration of substance that I mentioned. And we can see here, with the existence of the nanobubbles, even we put the same concentration of surfactant like SDS here, the surface tension of water can be reduced further together with the higher CO2 concentration and pH value comparing with the control one. The control here, I just would like to talk again, is just the same concentration of the substance we use and the gas suction time. We also suck the CO2 gas in there, but they're not in the form of nanobubble, they're just in the normal gas. And then we can see quite a significant difference between the existence and without the existence of the bubbles. And we also on the way to combine the nanobubbles with all the food nanomaterial. Here we use the carbon quantum dots. And we know that the icon, this one is CQD, the carbon dot. And with the just by the very simple technique, we use the microwave and glucose solution, and then we heat it up. And then we test with the specific time, and we can generate the quantum dot, which can very unique optical properties. And we hope that with the prominent or the optical characteristic like that, we can obtain the visible image of nanobubbles by just easily injecting the bubble inside this solution, inside the solution containing the quantum dots. Or we can use the quantum dots as another cover layer outside the nanobubbles and make it more stable, because actually the size of the quantum dot is just about 5 to 10 nanometer, where the gas bubble of us is about 200 to 400 nanometer. So if it can make another layer cover, and also it can have to improve the stability of the nanobubble throughout the application or the storage time. Or the system that we also set up now is the circulation one. The reverse one I mentioned is just the one injection, and it can continuous, and this one can continuous as well, but it's allowed to continue supply the gas through the membrane pore here, and then the liquid be circulated through the system by the pump with the specific time, and we also combine with the ultrasound level or energy to create the bubbles. And after preliminary tests, 3 variables or 3 factors with 3 different levels, we chosen is to optimum the bubble formations is the gas pressure within 1 to 3 bar, circulation time 5 to 15 minutes, and ultrasound level from 15 to 30 watt. It is the maximum one that the equipment can offer for us. And we use the response surface to optimize our setup. Then, as shown here, there is no significant effect of the ultrasound on the generation of the nanobubble, but gas pressure and circulation time they did. And with the aim to maximize the CO2 concentration and minimize the size of the bubbles, because even we would like the smaller size, we would like to keep the bubble at the smaller scale, so, diameter. So to optimum this target, the software it calculates for us is the gas pressure is 3 bar and circulation time is 30 minutes. And you can see the picture here, you see the normal water, don't have, it's just very clean water. And you see the nanobubble, it means the water contains the nanobubble generated by the optimum condition of the system. And because actually the bubble with very small or tiny size like that, the naked eye of us cannot see it, even they exist or not. So, but like you can imagine like the dust in the air, normal, as a generally, or it's just a normal situation, we cannot see. But if you have especially like some specific situation or specific light source, you can see they still exist in the medium and here as well. So with the optimum condition and the laser source light, we can see clearly the light, the green light of the light of the nanobubble that exists inside the liquid or the water medium, whether this we don't have. And then we use this condition to apply to other food liquid medium. Of course, they will have some difference, but we just basically set up from the water first, and then we apply, like we keep the 3 bar gas pressure, and then we try to vary the time of circulation. And with at some beginning step as well. So 2 type of solution we choose to test, and here's the sucrose solution at a 30% of concentration and 60% of the weight, and the other is the canola oil. One is a sucrose, is soluble in water, and the oil is insoluble. So with the good condition to generate CO2, and then with the 30% of sucrose solution, what we got? The obtained results show that they are all significantly reduced in the viscosity of the sucrose solution when the nanobubble inject inside them, even with just a very quick period, like just after the 5 minutes. And we continue to increase the circulation time, but actually the viscosity cannot be reduced further. This partly can be explained like because the concentration of CO2 is nearly saturated already, and the pH you can see clearly here compared with the control, the normal solution, the normal sucrose solution, the pH is dropped like lower than 4, while the control is just around 5.5. And the size in here, even we can treat with further time, we cannot change a lot. So at around 5 to 30 minutes, it also can get the significant reduction in the viscosity. And then for the sucrose solution at higher concentration, of course, with higher concentration, we got the higher viscosity value. And here we observe the higher reduction rates as well. And they're all significant lower than the control one. In here, we can obtain 10 to 12%. And all of them have the same total solid content. It means we not change anything in the 60% of the sucrose content in there. And the gas size distribution here, they have some, they show some difference. And you can see here with the further treatment time, it looks like the size of the gas or the size of the particle distribution in the medium is quite lower. It can be said, like just continue apply the CO2 in there, and then we observe some big gas bubble appear, and when because they big, so they easily to be flow up to the surface and be break, and maybe they can bring or make the loss of CO2 some part in there, and also affect the formation and the existence of the nanobubbles. So that's why the size distribution have different, and also it's quite not change a lot in the reduction rate of the viscosity for the sucrose solution. So how about the canola oil, which is insoluble in water? It have also the viscosity reduction, and the CO2 concentration in oil now, this can be up to 2000 ppm. So with because nanobubble is very small and they can exist a very long time into the medium. So with the high concentration, for example, is CO2 like that, it can maybe have to prevent the lipid oxidation as well. Or if you don't want to have the test, like because CO2 food grade, CO2 gas in the food grade type, they have the sour test. So if you don't want, maybe we can try with another gas like air or nitrogen. It's quite interesting as well. So now we can see quite clearly that the potential application of nanobubble in food-related process or product, like in the viscosity reduction effect, we know that the efficiency of the liquid food manufacture is limited by the high viscosity of materials, because high viscosity equals more power or operational cost to pump or to transfer liquid throughout the equipment. or even with the nanobubble, they can reduce or prevent the membrane fouling, which also helpful in the fractionation of some food process. And other, we can think like the means of seasoning food because they have quite small source, very high specific ratio, like surface per volume. So they can help to increase the solubility and the mass transfer as well, together with all the texture or like elasticity or sensory attribute of other food. Then yes, it's very interesting. We can look further into this novel and quite amazing technology. And we do believe that we can find the better, more sustainable result in the greener way, because nanobubble doesn't need to the support of the other chemical substance. So thank you very much for all of you for your kind attention. I would like to say my deep appreciation to my supervisors team and also Australia China Joint Research Center in Future Dairy Manufacture and Monash and UQ as well. Thank you so much, everyone.
Thank you, Ken, for our presentation. Due to the time limit, probably we take 1 or 2 questions. Is there any question? You can just unmute yourself and go ahead.
Young, I have a question for Khan.
Yes, please.
Khan, thank you for the nice presentation. I just want to ask, so a couple of questions. There were some studies coming out from the US, I think from Lloyd Metzger group, that looked at using CO2 to reduce viscosity of milk, but they're not using nanobubbles, just like injecting CO2 into the milk. Have you done studies to compare this performance from the nanobubble compared to just normal injection of CO2 to reduce viscosity for milk? And then the second question is, because you show that your viscosity actually slightly increased when you inject CO2 for longer time, and is that because you start to have coalescence of the bubbles?
Yep. Yes. Yes, so thank you very much for your question. Then for the first one, about the nanobubble resistance or circulation the CO2 can have or not with the viscosity. Actually, we try already with the circulation, but we not inject the gas, we just circulation with the time like that. Of course, it's not change. So, but it's a good idea as well with because we just inject the CO2 at the same time. The CO2 concentration cannot go up like that with the like 1,500 or 2,000 ppm. So we not measure the viscosity of just the normal injection or the normal circulation, but it's quite with the same characteristic and size distribution like that. It's not affect with the viscosity reduction. Yeah, so but I will try again because I circulation already and it doesn't change in viscosity value. I will check again with we just suction CO2, any membrane pore or any nanobubble forming. Let's see it can affect or not. But water with the same suction time, the CO2 of the water concentration is just about under 100 ppm, cannot go up to 2,000. Yeah. And for the second one, can you please?
I'm just wondering, because you show that your viscosity for the sucrose, for example, increased when you have your injection for about 50 minutes or something.
Yeah.
And is that because the longer that you get actually coalescence of the bubbles, and then that's kind of in fact affect your viscosity?
Yeah, because like we think that just 5 minutes is enough to reduce to the we can get the saturated level of the CO2 or the good side distribution of the bubbles to try to rather the longer time treatment it can have or not. But actually, when we just continue supply or inject the gas in there, the more and more of the big bubble appear. It's saturated and they cannot get the dissolubility higher or the CO2 higher. Then with the big bubble, and because they're big in size, so they easily to be come up to the surface. And if they up to the surface and they break up, then they will lose the CO2.
It's not effective.
Yeah. Thank you. Your question.
Thank you.
Thank you, Ken. I think we don't have more time for further question, but if you have question, you can leave a message or just email Ken. And I think we are going to finish our section here and going to the next activity. That's the closing remark from Cordelia.
Thank you, Yong. And I just want to quickly thank and because for everyone that are attending today. Thank you so much for your presence today. I know it is a very unusual way of conducting symposium, but maybe this is the new normal. We pretty happy with the way things goes, and hopefully you also find the symposium very useful. I just want to thank all the speakers today, especially our students. Some of them are finishing this year and they're going to be submitting very soon. And it's also a big achievement, especially under the current circumstances. I also want to thank Dr. Lin, who has helped us organize the whole symposium for today. And that's, again, it's not a very easy task because we were actually planning a number of activities, including a conference dinner tonight, but unfortunately we have to reschedule and rearrange everything because of the restriction that happened with the global pandemic. But again, I just want to thank everyone who are here today. And if you do have any questions with regard to anything that are being presented today, or about the center or any other queries, please let myself or Dr. Lin know. You have our contact. And through if you haven't received a copy of the newsletter, again, in the chat room, I think there's a link there, so you can have a look there. And yeah, we're also happy to take any feedback with regard to the symposium today. If you have any feedback that you want us to know, please let us know as well. And so thank you so much. And I just wish you a nice rest for the day, whether you're working or you are currently working from home or you already back in the office. I just hope that you have a good day for the rest of today. Thank you.
Thank you, Cordelia. Thank you, everyone.
So we can safely close the we can safely leave now, unless you want to make a chat. That's also okay. Thank you so much, everyone. Thank you.
Bye.
Bye.